What if I told you the universe is hiding its biggest secret in plain sight? Right now, as you watch this, an invisible force is stretching the cosmos apart at an accelerating rate, a force so mysterious, scientists call it dark energy. And here's the wildest part, we have no idea what it actually is. Think of it like the ultimate cosmic detective story, with clues scattered across billions of light years, and every answer we uncover only leads to deeper questions. From galaxies fleeing faster than light to voids in space that defy logic, dark energy isn't just a puzzle, it's a revolution waiting to happen in our understanding of reality itself. This isn't just some abstract scientific curiosity. Dark energy makes up about 68% of the universe, shaping everything from the fate of stars to the very fabric of spacetime. Yet, despite its overwhelming presence, it's completely invisible, undetectable by any instrument we've built so far. It's like trying to solve a murder mystery where the culprit leaves no fingerprints, no DNA, just a universe that's expanding faster and faster, as if something out there is playing by rules we can't even comprehend. And the stakes, nothing less than the ultimate fate of everything. Will the cosmos end in a fiery collapse, a frozen silence, or something even stranger? That's why today we're diving headfirst into 25 of the most mind-bending mysteries of the dark energy era, questions that keep astrophysicists up at night. We'll explore why some galaxies seem to be missing dark energy entirely, how empty voids in space might hold the key to cracking this enigma, and whether Einstein's equations might need a radical rewrite. Along the way, you'll witness bizarre cosmic phenomena that challenge everything we thought we knew, from phantom energies to universes bubbling into existence out of nothing. So buckle up, because this journey isn't just about uncovering secrets, it's about stepping to the edge of human knowledge and peering into the unknown. Ready to solve the universe's greatest mystery? Let's go. The story begins in 1998, when two teams of astronomers made a discovery so shocking it turned our understanding of the universe upside down. They were observing distant supernovae, exploding stars so bright they can outshine entire galaxies, hoping to measure how fast the cosmos was expanding over time. Conventional wisdom said gravity should be slowing everything down, like a ball tossed upward, gradually losing speed. But the data told a completely different story. Instead of slowing, the universe's expansion was accelerating, as if some invisible hand kept pressing harder on the cosmic gas pedal. It was like watching a car speed away faster and faster after you took your foot off the pedal, defying every law you thought you knew. This wasn't just a small discrepancy, it was a cosmic revolt, the only explanation, a mysterious, repulsive force counteracting gravity itself. Scientists called it dark energy, a placeholder for something they couldn't see, touch, or even fully describe. Imagine trying to explain the wind by watching leaves rustle but never feeling the breeze. That's the paradox of dark energy. Its effects are everywhere, yet its nature is utterly elusive. Even stranger, calculations showed this force wasn't just a minor player. It dominated the universe, making up over 2/3 of all existence. But here's where things get even weirder. If dark energy is pushing galaxies apart, why isn't everything ripped to shreds? Why do stars and planets hold together while the space between them stretches? The answer lies in the delicate balance of scales. Dark energy's push is weak on small distances, like a whisper lost in a hurricane, but over cosmic expanses, it adds up to an unstoppable shove. And the implications are staggering. If this acceleration continues, distant galaxies will eventually vanish from view, their light stretched too thin to reach us, leaving future astronomers with a sky full of darkness. Yet for all its strangeness, dark energy might not be the only explanation. Some theorists suggest Einstein's theory of gravity itself might need tweaking on cosmic scales, a radical idea, like finding out the rules of chess change halfway through the game. Others propose wilder possibilities, like hidden dimensions leaking energy into our universe. But one thing's certain, this mystery isn't just about distant galaxies. It's about rewriting the very laws that govern reality, and the deeper we look, the more questions we uncover. Why did dark energy turn on billions of years after the Big Bang? Is its strength constant, or could it change over time, leading to a cosmic fate we can't even imagine? The answers are out there, hidden in the dark. One of the most baffling things about dark energy is how stubbornly it refuses to fit into any neat category. Scientists have thrown every possible explanation at it, but none fully solve the puzzle. The frontrunner theory, Einstein's cosmological constant, a concept he once called his greatest blunder, only for it to make a triumphant comeback decades later. Imagine a numbers bet you placed and forgot about suddenly hitting the jackpot when you least expected it. That's essentially what happened here. The cosmological constant suggests dark energy is woven into the very fabric of space itself, a constant energy density that doesn't dilute as the universe expands. It's like an invisible spring embedded in reality, always pushing outward with the same relentless pressure. But there's a catch. When physicists calculate how strong this energy should be based on quantum theory, they get a number outrageously larger than what we observe, off by a factor of 1 with 120 zeros behind it. That's not just a rounding error, it's like predicting an ocean and finding only a single drop of water. This colossal mismatch is called the vacuum catastrophe, and it's one of the biggest unsolved problems in physics. Why does the observed dark energy have such an absurdly tiny value? Some think there's a hidden symmetry or cancellation mechanism we haven't discovered yet. Others suspect we might be asking the question all wrong. Then there's quintessence, dark energy's more dramatic cousin. Unlike the steady cosmological constant, quintessence proposes that dark energy is a dynamic field, ebbing and flowing over time. An idea inspired by ancient philosophers who believed the cosmos was governed by a fifth element beyond Earth: air, fire, and water. Picture a cosmic syrup slowly changing thickness, sometimes thickening to slow expansion, other times thinning to accelerate it. This could explain why dark energy seems to have turned on only a few billion years ago, as if something flipped a switch in the universe's history. But if quintessence is real, where's the evidence? The strangest part, both theories and dozens of others fit the data we have so far. It's like trying to identify a thief when every suspect leaves the same exact fingerprint. Without new observations, physicists are stuck in a debate with no clear winner. That's why teams are racing to build next-generation telescopes and satellites, hunting for tiny variations in the expansion rate or patterns in galaxy distributions that could tilt the scales toward one idea. Because here's the truth, dark energy isn't just some obscure detail in astrophysics. Its true nature could redefine everything from the birth of the universe to its final moments. Is it an unchanging constant, a shifting field, or something even more bizarre we haven't dreamed up yet? Until we know, the mystery remains wide open. Here's where dark energy's mystery takes a turn from puzzling to downright eerie. Everything about its behavior feels suspiciously convenient, as if the universe is following a script written just for us. Picture this: in the early cosmos, just after the Big Bang, matter and radiation were so dense that any trace of dark energy would have been drowned out. Gravity ruled supreme, pulling everything together to form galaxies and stars. But then, around 5 billion years ago, coincidentally right around the time Earth was forming, dark energy suddenly took center stage, overpowering gravity and kickstarting the universe's accelerated expansion. It's like living in an apartment where the heat mysteriously cranks up to unbearable levels the moment you finish building your ice sculpture. Why now? Why not earlier, when galaxies were still taking shape, or later, when the cosmos was on the verge of collapse? This bizarre timing is called the coincidence problem, and it's enough to make any physicist question whether they're missing something fundamental. Think of it as a cosmic version of Goldilocks' dilemma. Dark energy's influence isn't too strong to rip apart young galaxies, nor too weak to let gravity crush everything back into a singularity. It's just right for us to exist and notice it. But in a universe that's over 13 billion years old, the odds of us being around during this sliver of time when dark energy and matter are balanced in such a delicate way seem astronomically low. It's like winning the lottery every single day for a lifetime and then wondering if the game is rigged. Some scientists argue this isn't a coincidence at all, it's a clue. Maybe dark energy isn't constant but evolves in sync with the universe's structure, fine-tuning itself in ways we don't yet understand. Others propose an even wilder idea. What if we're seeing evidence of a multiverse where countless universes exist with different dark energy strengths, and we just happen to live in one where the numbers allow galaxies and life to form? Imagine walking into a library with infinite books, where each volume tells the story of a universe with slightly different rules. Most of those stories end too quickly for anything interesting to happen, but a rare few, like ours, hit the sweet spot. And then there's the unsettling possibility that dark energy's current dominance isn't permanent. If it's a field that can decay or strengthen over time, the universe's fate could swing from runaway expansion to catastrophic collapse, or something entirely unpredictable. The one thing all these theories share, they force us to confront a humbling truth. We might not just be discovering the laws of the cosmos, but witnessing the conditions that made our existence possible in the first place. So the next time you look up at the night sky, remember, you're not just seeing stars, you're seeing a mystery written in the fabric of time itself, one that might hold the key to why we're here at all. What if the real mystery isn't dark energy, but gravity itself? For decades, scientists have assumed Einstein's theory of general relativity holds true everywhere, from the fall of an apple to the dance of galaxies. But what if gravity plays by different rules on cosmic scales, and we've been misreading the universe's expansion all along? This isn't just a wild thought experiment. A small but passionate group of physicists argues that dark energy might be a mirage, a cosmic illusion created by our incomplete understanding of how gravity truly works. Take modified Newtonian dynamics, or MUND, for example. This theory suggests that gravity doesn't fade as quickly over vast distances as Newton or Einstein predicted. Instead, it tugs on stars and galaxies with an extra, unseen hand, like a hidden current subtly steering a river's flow. MUND was originally proposed to explain why galaxies rotate faster than expected without invoking dark matter, but some researchers have stretched the idea further, applying it to cosmic expansion. If gravity's grip weakens less than we thought over enormous voids between galaxies, it could mimic the effects of dark energy, making the universe appear to accelerate when it's really just gravity behaving oddly. Then there's FR gravity, a mouthful of a theory that tweaks Einstein's equations to allow gravity's strength to vary depending on the curvature of spacetime. Picture a rubber sheet that stiffens or softens in different regions, altering how objects roll across it. In some versions of this model, the universe's expansion could speed up without any dark energy at all, just by gravity, leaking into hidden dimensions or shifting its rules over time. It's like discovering the brakes on your car occasionally turn into accelerators depending on where you're driving. So why hasn't the scientific world abandoned dark energy for these alternatives? The answer lies in the data. While modified gravity theories can explain some observations, they stumble over others. For instance, the cosmic microwave background, the afterglow of the Big Bang, shows patterns that match dark energy's influence precisely. And when astronomers map the large-scale structure of the universe, the way galaxies cluster and voids form aligns perfectly with dark energy's push, not modified gravity's tweaks. It's like trying to solve a jigsaw puzzle where most pieces fit one picture, but a handful stubbornly suggest another. But the debate is far from over. Modified gravity still offers one tantalizing advantage. It avoids the vacuum catastrophe, that infamous mismatch between predicted and observed dark energy strength. If gravity's laws are simply more flexible than we realized, the universe's acceleration might not require any mysterious energy at all. That's why experiments like the European Space Agency's Euclid telescope are hunting for tiny deviations in gravity's behavior across cosmic history, clues that could tip the scales toward a revolution in physics. For now, dark energy remains the leading explanation, but the very fact that alternatives exist tells us something profound. Science thrives on questions, not absolutes. Whether the answer lies in an invisible force or rewritten laws of gravity, one thing's certain: the universe still has secrets to spill, and the next breakthrough might not come from confirming what we think we know, but from daring to question it. There's a crack in our cosmic map, a discrepancy so stubborn it's splitting modern cosmology down the middle. Meet the Hubble Tension, a 10% gap between how fast different methods say the universe is expanding. On one side, measurements of nearby galaxies and supernova peg the Hubble constant at around 73 kilometers per second per megaparsec. On the other, the cosmic microwave background, the faint glow from the infant universe, suggests a slower 67. At first glance, that difference might seem trivial, like arguing whether a car's speed is 65 or 70 miles per hour. But in cosmology, where precision dictates reality's rules, this gap is seismic. It's like two clocks ticking at different rates in the same room, and no one can figure out why. The plot thickens when you realize both methods are bulletproof in their own ways. The local measurements, using pulsating stars and exploding supernova as cosmic yardsticks, have been refined for decades. Meanwhile, the cosmic microwave background data from missions like Planck is so exquisitely detailed it's often called the gold standard of cosmology. Yet they refuse to agree. Imagine two master chefs following the same recipe but ending up with entirely different dishes, one a cake, the other a loaf of bread. Either someone missed a secret ingredient or the recipe itself changes when we're not looking. Could dark energy be that phantom variable? Here's where things get speculative and thrilling. If dark energy isn't a constant but a force that's evolved over time, it might have tweaked the universe's expansion rate in ways we haven't accounted for. Picture a rocket whose thrusters mysteriously gain power mid-flight, throwing off pre-launch speed predictions. Some theories suggest dark energy could have kicked in more strongly in the last few billion years, accelerating certain regions of space faster than others. That would mean our local measurements capture a speedier, modern universe, while the cosmic microwave background reflects an older, slower era. It's like comparing a sprinter's speed at the starting gun to their final dash, except no one told us the race had variable rules. But not everyone's convinced dark energy is the culprit. Alternative explanations range from undiscovered particles subtly influencing cosmic growth to hidden flaws in how we measure distances across the void. There's even a fringe idea that our galaxy sits in a bizarrely underdense region of space, a cosmic bubble that skews our perspective, like being the only quiet corner in a roaring stadium. The more we dig, the clearer it becomes. The Hubble tension isn't just a math error. It's either the first whisper of a cosmological revolution or a sign we've been reading the universe's script all wrong. What makes this mystery so urgent is its stakes. If the discrepancy stems from dark energy's evolution, it means our universe's expansion isn't just accelerating, it's doing so unpredictably, like a car with a faulty gas pedal. That could rewrite everything from galaxy formation to the cosmos's ultimate fate. But if the answer lies elsewhere, in new physics or measurement biases, it's equally transformative. Either way, the Hubble tension isn't just a puzzle to solve. It's a wake-up call that the universe might be far stranger than our textbooks dared to suggest. Picture a force so powerful it could shred the universe down to its last atom, not in billions of years, but in a sudden, violent instant. This isn't science fiction. It's a real possibility lurking in the shadows of dark energy research, known as phantom energy. Unlike ordinary dark energy, which pushes galaxies apart at a steady pace, phantom energy grows stronger over time. It's the difference between a gentle breeze and a hurricane that keeps intensifying, where every gust of wind makes the next one even fiercer. If this nightmare scenario is real, the cosmos could face a fate more dramatic than anything we've imagined: the Big Rip. Here's how it would unfold. First, the accelerating expansion would overcome gravity's grip, flinging galaxies away so fast their light could never reach us again. Next, the phantom energy's intensifying pull would tear apart galaxy clusters, then individual galaxies, until stars themselves were ripped from their orbits. But it wouldn't stop there. In the final moments, even atoms and subatomic particles would be stretched beyond their limits, snapping the very fabric of matter. The universe wouldn't just fade into cold darkness, it would explode into nothingness, like a piece of paper torn into smaller and smaller fragments until only dust remains. Yet for all its horror movie potential, the Big Rip isn't guaranteed. Current observations suggest dark energy behaves more like Einstein's cosmological constant, steady and unchanging. Phantom energy, by contrast, would leave fingerprints in the way supernova brighten and dim over cosmic distances, or in subtle shifts in the cosmic microwave background. So far, those signals haven't shown up conclusively. It's like hearing whispers of a storm but never feeling the wind. But the absence of evidence isn't evidence of absence. Some theories suggest phantom energy could be hiding in plain sight, its effects too subtle to detect. Yet, others argue it might not kick into overdrive until the universe is much older, like a time bomb set for trillions of years in the future. And then there's the chilling thought that if phantom energy exists, its growth could be exponential, meaning we might not recognize the danger until it's too late to study it. The scariest part, we're not just passive observers in this drama. If the Big Rip is real, it could happen sooner than anyone expects. Some calculations suggest a phantom-dominated universe might have as little as 20 billion years left, a blink of an eye in cosmic terms. That's why scientists are racing to map dark energy's behavior with unprecedented precision, using tools like the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope. Because if phantom energy is out there, we're not just uncovering another mystery of the cosmos, we're reading our own expiration date, and that changes everything. Imagine you're holding a calculator, punching in the numbers for the universe's most basic energy, the hum of empty space itself. According to quantum physics, even a perfect vacuum isn't truly empty. Particles flicker in and out of existence, creating a seething, invisible ocean of energy. Now, here's where the math goes off the rails. When theorists calculate how much energy this quantum foam should contain, the answer is a number so absurdly large it's almost comical, one followed by 120 zeros. That's more energy than exists in all the stars, galaxies, and black holes combined, multiplied by a factor beyond comprehension. And yet, when we measure dark energy's actual strength, it's barely a whisper in comparison. This isn't just a slight miscalculation. It's the most embarrassing mismatch in the history of science. So what's going on? One possibility is that dark energy is the ghostly remnant of this quantum frenzy, diluted over cosmic time like a fading echo. Picture a roaring waterfall reduced to a single drop, except no one can explain where all that water vanished. Some theorists suggest that extra dimensions or exotic symmetries might cancel out most of the vacuum's energy, leaving behind the faint trace we call dark energy. Others propose that the universe's expansion somehow screens this energy like a cosmic filter, letting only a tiny fraction through. But these ideas are just placeholders for a deeper truth we haven't grasped yet. The real shocker: if vacuum energy had turned out as strong as predicted, galaxies could never have formed. The universe would have blown itself apart instantly after the Big Bang. The fact that we exist means something, whether luck, undiscovered physics, or a cosmic fine-tuning beyond our understanding, is keeping this energy in check. It's like discovering your car's engine should have exploded 1,000,000 times over, yet somehow it's still running smoothly. This isn't just academic curiosity. If dark energy is connected to vacuum energy, it could mean we're on the brink of a quantum gravity revolution, a theory bridging the tiny world of particles and the vastness of spacetime. Until then, the vacuum catastrophe stands as both a humbling reminder of how much we don't know and a beacon pointing toward the next great breakthrough. The universe isn't just hiding its secrets, it's daring us to solve them. Imagine if the universe's greatest mystery wasn't just unexplained, it was impossible. That's the bombshell dropped by string theorists with their so-called swampland conjectures, a set of mathematical rules suggesting stable dark energy shouldn't exist at all. According to these ideas, our leading explanation for cosmic acceleration, Einstein's cosmological constant, might be banished to the swampland, a theoretical no-man's land where self-consistent physics goes to die. It's like building a house on quicksand. The math works at first glance, but the deeper you dig, the less stable it becomes. String theory, the ambitious framework aiming to unify all forces of nature, paints a universe far more rigid than we've observed. One of its core conjectures states that any stable vacuum energy, like the kind dark energy seems to embody, must either be zero or enormous, with no in-between. But our measurements show dark energy as a tiny, non-zero value floating in that forbidden middle ground. This isn't just a discrepancy, it's a full-blown crisis. Think of it like a traffic law declaring no speeds between 30 and 70 miles per hour while you're cruising at 50. Either the law's wrong or you're breaking it, and in this case the universe itself might be the violator. So why would string theory impose such strict rules? It all ties back to how the theory handles extra dimensions. In string theory's labyrinth of higher dimensional spaces, certain configurations are stable, while others inevitably decay or collapse. Dark energy's observed strength falls into the unstable zone. Like a pencil balanced on its tip, it should topple, yet somehow it hasn't. Some theorists argue this means we're missing a critical piece, like undiscovered fields or dynamic mechanisms that stabilize the instability. Others propose darker alternatives. Maybe we're witnessing the slow unraveling of a metastable universe, like a bridge swaying before its eventual collapse. But here's where observations throw a wrench into the debate. If dark energy were truly unstable, we'd expect to see its strength fluctuate over time, yet current data suggests it's eerily constant. This leaves physicists at a crossroads. Either string theory's swampland conjectures need revising, or dark energy isn't what we think it is. A third, even wilder possibility. Our patch of the universe is a rare bubble in an otherwise chaotic multiverse, where the rules bend just enough to allow our existence. Picture winning a cosmic lottery where the prize is a universe that shouldn't work, but does. The implications are staggering. If string theory's constraints hold, dark energy might not be a constant force but a fleeting phase, destined to decay into something else entirely. Alternatively, we might need to abandon cherished assumptions about quantum gravity altogether. For now, the swampland remains a battleground between theory and observation, where every new telescope or particle collider brings us closer to an answer. One thing's certain: if the universe is breaking the rules, the ultimate cosmic rebellion is happening right under our noses, and we're only beginning to grasp the consequences. Dark energy doesn't just push galaxies apart, It's actively reshaping the cosmic landscape, leaving behind a trail of stunted structures frozen in time. Picture a gardener pruning a tree, but instead of encouraging growth, they're silently snipping away the branches before they can fully form. That's what dark energy does to galaxy clusters, the universe's largest gravitationally bound structures. Without it, these colossal assemblies of hundreds or even thousands of galaxies would continue merging, growing ever more massive over billions of years. But dark energy's relentless push has put the brakes on this process, like an invisible hand pressing against the universe's ambition to build. The evidence comes from comparing supercomputer simulations with real telescope observations. When researchers run models of cosmic evolution without dark energy, they predict a universe teeming with gargantuan galaxy clusters, some weighing in at over 1 quadrillion times the mass of our Sun. But when they overlay actual sky surveys, like the Sloan Digital Sky Survey or Chandra X-ray observations, the numbers don't match. The clusters we see are smaller, fewer, and more spread out, as if something interrupted their growth spurt halfway through. It's like excavating an ancient city and finding half-finished temples, their pillars never reaching the intended height. The strangest part, this suppression isn't uniform. Dark energy's grip is weakest where matter is densest, meaning some clusters still manage to grow in the densest knots of the cosmic web, but the voids between them, those are where dark energy reigns supreme. Over time, these empty regions stretch faster and faster, pulling galaxies away from each other like raisins in an expanding loaf of bread. Except the loaf is growing so quickly that the raisins can no longer clump together. The result is a universe where structure formation peaks and then declines, like a civilization that built its grandest monuments early, only to watch later generations struggle with dwindling resources. This cosmic slowdown leaves behind subtle fingerprints. One telltale sign is the way clusters distribute their hot gas. Normally, gravity heats this gas to millions of degrees as it collapses, creating bright X-ray halos. But in a dark energy-dominated era, simulations show these halos should be fainter and more diffuse, exactly what telescopes detect. Another clue lies in the splashback radius, the boundary wherein falling galaxies start orbiting a cluster rather than merging into it. Dark energy's push makes this boundary sharper, like a shoreline eroded by an unrelenting tide. Yet for all these insights, mysteries linger. Why do some clusters, like the El Gordo system in the distant universe, appear too massive for dark energy's constraints? Could there be pockets where gravity still holds sway, or are we misreading the data entirely? The answers might lie in next-generation instruments like the James Webb Space Telescope and the upcoming Euclid mission, which will peer deeper into the cosmic web than ever before. Because every stunted cluster, every stretched void, is a message from the darker cosmic drama written in the language of gravity's defeat. And deciphering it could reveal not just how structures form, but how the universe itself chooses its winners and losers. One day, far in the future, the last visible remnant of the Big Bang will vanish, not with a bang but a whisper. The cosmic microwave background, that faint glow illuminating the infant universe, will stretch into oblivion as dark energy accelerates the cosmos beyond recognition. Right now, we see this radiation as microwave static, a snapshot from 380,000 years after creation. But given enough time, trillions upon trillions of years, every photon in that signal will redshift into undetectable radio waves, then fade into silence. It's like watching a photograph slowly bleach in sunlight, losing detail until only blankness remains. This isn't just theoretical, the physics is mercilessly clear. As space expands, light waves stretching across it lose energy, sliding from visible colors to infrared, then to microwaves, and eventually to wavelengths longer than the observable universe itself. For the cosmic microwave background, that process is already underway. Today, its photons arrive with wavelengths about 1 millimeter long in 100 billion years. They'll stretch to the length of a football field. Fast forward another trillion, and those same signals could span entire solar systems far too faint and spread out for any conceivable detector to spot. The irony is brutal. The very expansion dark energy drives will ultimately erase the evidence we need to study it. But the real tragedy lies deeper. The cosmic microwave background isn't just data, it's our only direct window into the universe's beginnings. Without it, future civilizations might never deduce the Big Bang even happened. Imagine archaeologists trying to reconstruct an ancient city after every brick has crumbled to dust. All they'd see is an endless, featureless void, with no clues that stars, galaxies, or cosmic structures ever existed. That's the fate awaiting any observers in the distant future. The universe won't just be expanding, it'll be actively hiding its own history. Yet even this grim scenario has a twist. Some theorists suggest that advanced civilizations might still piece together cosmic origins by studying hyper-redshifted gravitational waves or quantum imprints in spacetime itself. It's like trying to identify a fire by feeling the warmth of its ashes long after the flames have died. Others propose that the cosmic microwave background's disappearance could actually help reveal dark energy's true nature, much like how shadows grow sharper as light fades. If dark energy's strength changes over time, its effects on the stretching of space might leave subtle patterns in the last detectable remnants of the background radiation. For now, we're privileged to live in a brief cosmic era where the past is still visible. The real question isn't just what we'll lose when the cosmic microwave background vanishes, but what secrets we can wrest from it before the lights go out for good. What if dark energy isn't just a random feature of our universe, but the reason we're here to observe it? This idea, known as the anthropic principle, flips the mystery on its head. Instead of asking why dark energy has the value it does, it suggests the answer might be simple. If it were any different, we wouldn't exist to wonder about it. Picture a universe where dark energy's strength is 10 times higher. Galaxies would never form, ripped apart by expansion before stars could ignite, 100 times weaker. Gravity would have crushed everything back into a singularity long ago. Our universe seems precariously balanced on a knife's edge, and that's where the multiverse theory comes roaring in. Imagine a cosmic lottery with infinite tickets, each representing a separate universe with randomly dialed physical constants. Most of those universes would be barren, with dark energy too weak or too strong to permit galaxies, planets, or life. But a tiny fraction, purely by chance, land in the Goldilocks zone. We don't live in a special universe. We live in the only kind of universe where beings like us could evolve to notice it. It's like a puddle marveling at how perfectly the hole it sits in fits its shape. The hole wasn't made for the puddle simply filled what was there. But is this explanation science or philosophy? Critics argue the anthropic principle is a cop-out, a way to dodge deeper questions about why our laws of physics exist as they do. After all, invoking a multiverse doesn't explain why universes vary in the first place, it just kicks the mystery up a level. Others counter that it's no different from accepting Earth's distance from the Sun as a precondition for life. We don't call that coincidence, we call it astronomy. The difference, we can see other planets orbiting at different distances, while other universes remain hypothetical. Yet there's a tantalizing middle ground. Some theories, like string theory's landscape, predict a vast array of possible universes with different constants emerging naturally from quantum fluctuations. In this view, the multiverse isn't an untestable fantasy, it's a mathematical consequence of deeper physics. And while we can't hop between universes yet, their existence might leave subtle fingerprints in our own. Anomalies in the cosmic microwave background, for example, could hint at collisions with other bubble universes in the distant past. The stakes couldn't be higher. If the anthropic principle holds, dark energy's value isn't a puzzle to solve but a selection effect, one thread in a tapestry of infinite possibilities. But if it's wrong, we're back to square one, staring at a cosmic dial tuned with inexplicable precision. Either way, the question forces us to confront the limits of science itself. Are we uncovering the universe's rules or just reading the fine print of our own existence? The answer might redefine not just dark energy, but our place in the grand scheme of everything. The cosmic microwave background should be a perfect snapshot of randomness, a relic glow from the Big Bang that looks the same in every direction. But when researchers mapped its temperature fluctuations with unprecedented precision, they stumbled on something that defies expectations, an eerie alignment of hot and cold spots along a single axis, nicknamed the axis of evil. This isn't just a statistical fluke. The odds of such a pattern appearing by chance are less than 1 in 1,000, like rolling the same number on a die 20 times in a row. And here's the unsettling part. This axis bizarrely aligns with the plane of our solar system, and the direction the universe appears to be expanding, as if dark energy itself has a preferred direction, a cosmic North Star guiding its push. Think of it like walking into a room where every painting hangs crooked, all tilted toward the same corner. You'd assume someone or something arranged them that way deliberately. But in a universe where the fundamental laws are supposed to be identical everywhere, this directional bias makes no sense. It's as if the cosmos has a hidden spine, and we're seeing the first fractures in our assumption that space treats all directions equally. Some theorists argue this could mean dark energy isn't uniform but flows like a river, stronger in some regions than others. Others suggest it might be evidence of a pre-Big Bang structure imprinted on reality, like scars from a collision with another universe. The controversy deepens when you consider how this axis aligns with other cosmic anomalies. The distribution of galaxies in certain surveys seems to echo this preferred direction, as if the universe's large-scale structure is whispering the same secret. Even more perplexing, the so-called dark flow, where hundreds of galaxy clusters appear to stream toward a single point beyond the observable horizon, a motion that defies conventional explanations. Could these all be pieces of the same puzzle, hinting that dark energy's influence isn't just a steady push but a directional force sculpting the cosmos in ways we've barely begun to grasp? Skeptics counter that the axis of evil might simply be an artifact of measurement errors or foreground interference from our own galaxy. After all, peeling away the Milky Way's haze to reveal the pristine cosmic microwave background is like trying to listen to a whisper in a hurricane. But even after accounting for these effects, the anomaly persists, gnawing at the foundations of modern cosmology. If dark energy truly has a preferred direction, it would upend one of Einstein's core principles, that the universe has no special vantage point, no center, no edges. Future missions like the Lightbird satellite aim to test this anomaly with even finer precision, hunting for patterns that could confirm or dismantle the axis of evil's reality. Because if it's real, we're not just revising a footnote in astrophysics, we're rewriting the story of how the universe expands, and perhaps even uncovering clues about what existed before the Big Bang. The cosmos might not be the featureless void we imagined, but a place with hidden landmarks pointing toward mysteries deeper than we ever suspected. What if dark energy isn't some exotic force, but the hidden heartbeat of the quantum world echoing across the cosmos? At the smallest scales, particles flicker in and out of existence, entangled in a dance where their fates are inexplicably linked no matter how far apart they drift. Now imagine that same bizarre connection, but stretched to galactic proportions, where entangled particles spanning entire galaxies might be generating dark energy as a cosmic side effect. It sounds like science fiction, but some physicists argue this could be the key to cracking one of the universe's toughest puzzles. Take the holographic principle, for instance, a radical idea that suggests our three-dimensional reality might be a projection of information encoded on a two-dimensional surface, like a cosmic version of a banknote security hologram. In this mind-bending framework, dark energy could emerge from the way quantum information scrambles and stretches across the universe's boundary. Picture a balloon expanding. As the surface area grows, the quantum pixels storing reality's data stretch thinner, creating tension that manifests as dark energy's repulsive push. It's as if the universe is constantly recalculating its own code, and the energy required to maintain that operation is what we're detecting as cosmic acceleration. But quantum entanglement offers an even wilder possibility. Normally, entangled particles like two coins that always land on opposite sides, no matter how far apart they're flipped, only influence each other on tiny scales. But what if entanglement isn't confined to particle pairs? What if entire regions of space-time are quantum-linked, with galaxies acting like supercharged entangled systems? Every time two galaxies drift apart, their entangled state could release energy into the fabric of space itself, gently prying the universe open. Think of it like a cosmic version of stretching a rubber band. The farther you pull, the more energy builds up in the tension. The math behind these theories is still in its infancy, but early models hint at something extraordinary. If quantum entanglement scales up to cosmic proportions, it could explain why dark energy's strength is so bafflingly weak compared to predictions. At the quantum level, particles interact in a frenzy of energy, but when that activity gets smeared out across vast distances, the effect might dilute into the faint background hum we observe. It's like taking the roar of a jet engine and spreading its sound waves across an entire ocean. What's left is just a whisper, but a whisper that shapes the fate of everything. Critics argue these ideas stretch quantum mechanics beyond recognition into realms where no experiment can yet reach. But supporters counter that dark energy's very existence already defies conventional physics, so why not consider solutions as bold as the problem itself? Upcoming experiments aiming to measure quantum entanglement over record distances or probe the holographic nature of space-time could tilt the scales. After all, if the universe is truly a quantum system at heart, then the answers we're seeking might not lie in some mysterious force, but in the invisible thread stitching reality itself together. The more we pull on those threads, the closer we get to unraveling the universe's deepest secret. Right now, the night sky is a glittering archive of cosmic history, a tapestry of galaxies, stars, and the faint glow of the Big Bang itself. But dark energy is quietly rewriting that story, erasing the universe's past like pages fading in sunlight. Fast forward 1 trillion years and the view from Earth, or whatever planet might harbor life then, will be unrecognizable. The same force accelerating the cosmos will have pushed every galaxy beyond our horizon, isolating us in an ocean of darkness so vast future astronomers might never know the universe had a history. Picture a ship stranded in the middle of the ocean, watching the last distant sail vanish over the horizon. No matter how powerful your telescope, you'd never know other ships existed, only endless, featureless water. That's the fate awaiting any civilization born in the far future. As dark energy stretches space faster than light can traverse it, galaxies beyond our local cluster will redshift into invisibility, their light stretched so thin it dissolves into nothingness. The cosmic microwave background, our last relic of the Big Bang, will have long since faded into undetectable radio silence. Even the evidence of expansion itself, the redshift of distant galaxies, will be lost because there'll be no distant galaxies left to observe. Future scientists might measure a seemingly static, eternal void, unaware that trillions of stars once blazed beyond their vision. The cruel irony, the very expansion that makes the universe hospitable today, giving galaxies room to form and lifetime to evolve, will eventually render the cosmos incomprehensible. Imagine growing up in a house where the walls slowly recede each year, until one day you wake up to find yourself in an empty field with no memory of the rooms that once surrounded you. That's the paradox. Dark energy's gentle push allowed complexity to arise, but its long-term victory will erase all traces of how it happened. Here's where the mystery deepens. If future civilizations can't see other galaxies or detect the cosmic microwave background, how would they even suspect the universe had a beginning? Without clues like Hubble's law or the abundance of light elements evidence tied to galaxies and the Big Bang's aftermath, they might conclude the cosmos is eternal and unchanging, like an infinite, starless void. It's a staggering thought. The tools we take for granted, from redshift surveys to the glow of the cosmic microwave background, are temporary gifts of this brief cosmic era. Yet some theorists propose there might be other ways to uncover the truth. Gravitational waves from long-merged black holes could persist as faint whispers in spacetime, hinting at a violent past. Or perhaps the subtle quantum imprints of inflation frozen into the fabric of reality might still be detectable with technology far beyond ours. It's like piecing together an ancient civilization not from its crumbled monuments, but from the radioactive decay of long-vanished tools. But the most haunting possibility, we might be the only generation of observers who can see the universe as it truly is, a dynamic, expanding cosmos rich with history. Billions of years from now, when the last distant galaxy winks out of view, the universe's greatest story could become its best-kept secret. And that raises a chilling question. If we've already missed our universe's equivalent of ancient, fading clues, how much have we already lost to time? What if dark energy's greatest secret isn't in our universe at all, but hiding just beyond it? Some of the wildest theories in physics suggest this mysterious force might be spilling into our reality from hidden dimensions, like water seeping through cracks in a dam. The idea builds on string theory's proposal that our familiar three-dimensional space could be just one layer of a much richer cosmic cake, with up to 11 dimensions curled up so tightly we've never detected them. If even a fraction of dark energy's power is leaking into these unseen realms, it could explain why the force appears so bafflingly weak in our slice of reality. Think of it like trying to hear a concert from outside the stadium. You might catch faint echoes of the music, but most of the sound stays trapped inside. Similarly, if dark energy's true strength is spread across multiple dimensions, what we perceive might just be the faintest ripple reaching our three-dimensional world. This wouldn't just solve the vacuum catastrophe, that infamous mismatch between predicted and observed dark energy strength. It could rewrite our understanding of gravity itself. After all, if gravity is also leaking into extra dimensions, as some models suggest, its apparent weakness compared to other forces might share the same cosmic loophole. But how could we possibly test such a mind-bending idea? One clue might come from gravitational waves. When black holes collide, they send ripples through space-time, ripples that could carry imprints of extra dimensions if those dimensions affect how gravity propagates. Imagine tossing a pebble into a pond and seeing not just circular waves, but faint, geometric patterns hinting at hidden currents beneath the surface. Experiments like LIGO and future space-based detectors could hunt for these anomalies, searching for tiny deviations in gravitational wave signals that defy four-dimensional physics. Even stranger, certain models predict that extra dimensions might not be static, but dynamic, stretching or compressing over time. If dark energy is tied to these shifting dimensions, its strength could fluctuate across cosmic history, leaving fingerprints in the large-scale structure of the universe. It's like discovering that your house's foundation isn't solid concrete, but a living, breathing membrane that subtly changes shape when you're not looking. Critics argue that extra dimensions remain speculative, with no direct experimental proof. But supporters counter that dark energy itself is evidence of something beyond our current physics, and the most elegant solutions often lie in the least expected places. Whether these hidden dimensions exist or not, their mere possibility forces us to confront a humbling truth. The universe may be far grander and far weirder than the sliver we call home. And if we're right about the leaks, we're not just solving a mystery, we're peeling back the very fabric of reality. When scientists launched the Dark Energy Survey, they expected to map the fingerprints of cosmic expansion. But what they found instead was a universe behaving like a perfectly tuned instrument, playing notes no one predicted. This ambitious project, scanning 1/8 of the sky with unprecedented precision, revealed that matter isn't clumped the way our best models said it should be. Instead of finding dense knots of galaxies surrounded by vast cosmic voids, the survey uncovered a distribution of matter so smooth it almost defies logic. Imagine shaking a snow globe and expecting chaotic swirls, only to watch the flakes settle into unnervingly even layers. That's the level of surprise we're talking about. The implications ripple across cosmology. According to Einstein's general relativity, gravity should have sculpted matter into sharper peaks and deeper valleys over billions of years. Dark energy's repulsive push ought to enhance this effect, stretching voids wider while leaving galaxy clusters more tightly packed. But the Dark Energy Survey's data tells a different story, one where the cosmos looks suspiciously well mixed, like a barista perfectly frothing milk into coffee. Some researchers suggest this could mean dark energy interacts with matter in ways we've never accounted for, perhaps exerting a subtle drag that prevents clumping. Others wonder if our understanding of gravity itself needs revision on scales larger than galaxies. Even stranger is how this smoothness aligns with other cosmic anomalies. The same regions where matter appears unexpectedly evenly distributed also show peculiar flows of galaxies' movements that can't be explained by the gravitational pull of visible structures alone. It's as if invisible currents are stirring the cosmic soup, keeping everything just blended enough to unsettle our theories. One provocative explanation. Dark energy might not be uniform but clustered in unseen patterns, like submerged reefs redirecting the flow of an ocean. If true, this would turn our notion of dark energy as a featureless background force upside down. Yet the most tantalizing clue lies in the survey's measurement of cosmic shear, the way light bends as it travels through the universe's web of matter. The distortions were weaker than expected, suggesting that either dark energy is suppressing the growth of cosmic structures more aggressively than predicted, or that matter is spread more thinly than our models allow. Picture building a suspension bridge where the cables mysteriously sag less than your blueprints calculated. You'd either question your understanding of tension or suspect someone added invisible supports. For now, the Dark Energy Survey's puzzles remain open questions, but they're far from dead ends. Each anomaly is a breadcrumb leading toward a deeper truth, whether it's hidden facets of dark energy, unseen dimensions influencing gravity, or flaws in our cosmic yardsticks. Upcoming telescopes like the Vera Rubin Observatory aim to resolve these discrepancies with even finer precision. Because when the universe hands you a smoothie instead of the chunky salsa you ordered, it's not a mistake, it's a message. And deciphering it might just rewrite the recipe of reality itself. What if dark energy isn't a constant force, but a cosmic chameleon shifting its strength over time? The Standard Model treats it like an unwavering pressure, Einstein's cosmological constant, but some astronomers are gathering evidence that suggests otherwise. Picture a river that sometimes flows gently and other times rushes violently, yet you've only ever seen it at noon. That's the risk we face by assuming dark energy's behavior is uniform across billions of years. The first whispers of variation came from supernova data, when researchers compared ancient stellar explosions billions of light years away with more recent ones. Some teams reported subtle discrepancies in how brightness faded over time, hinting that dark energy's push might have been weaker in the universe's youth. It's like finding two identical cars accelerating at different speeds despite having the same engine. Follow-up studies using baryon acoustic oscillations, frozen ripples in galaxy distributions from the early cosmos added fuel to the fire. These cosmic yardsticks suggested the universe's expansion didn't quite match predictions if dark energy were truly constant. Then came the real curveball, measurements of quasars, ultra-bright galactic cores powered by supermassive black holes. By analyzing how their light interacts with intergalactic gas clouds over cosmic time, one controversial study claimed dark energy's strength might have peaked around 8 billion years ago, like a cosmic bell curve rather than a flat line. Skeptics argue these signals could stem from systematic errors or unaccounted dust in distant galaxies, but if verified, the implications would be staggering. A time-varying dark energy could mean we're witnessing a transitional phase in the universe's evolution, like a pendulum swinging toward some unseen equilibrium. The most radical interpretation, dark energy might be decaying, slowly transforming into something else entirely. Some theories propose it could be dissolving into dark matter, or even fueling the birth of invisible parallel universes beyond our detection. Others suggest its fluctuations could be tied to cyclic cosmological models, where the Big Bang was just one episode in an endless loop of expansions and contractions. Imagine the universe breathing in and out, with dark energy as its lungs, sometimes exhaling aggressively, other times pausing to inhale. For now, the evidence remains tantalizing but inconclusive. Upcoming projects like the Dark Energy Spectroscopic Instrument aim to settle the debate by mapping 35 million galaxies and quasars across 11 billion years of cosmic history. Because if dark energy is changing, we're not just studying a force, we're watching the universe rewrite its own rules in real time, and that changes everything. Black holes might be the universe's most efficient vaults, not just trapping light and matter, but locking away the very energy fueling cosmic expansion itself. This bizarre idea flips conventional wisdom on its head, suggesting these gravitational monsters aren't just passive consumers of space-time but active players in the dark energy saga. Picture a bank where deposits don't just sit in vaults but grow exponentially, secretly funding the economy outside. That's the role some physicists now propose for black holes in the dark energy puzzle, tying together two of cosmology's greatest mysteries in a single breathtaking theory. The connection hinges on vacuum energy, the same quantum froth that might underlie dark energy. According to general relativity, black holes warp spacetime so severely that they could effectively store this energy in their event horizons, preventing it from dissipating into the wider cosmos. It's like a cosmic dam holding back a reservoir with the energy trapped at the edges instead of flooding outward. But here's where Hawking radiation complicates things. As black holes slowly evaporate, they release particles and, theoretically, the energy tied to their horizons. If this energy is linked to vacuum fluctuations, it could mean black holes aren't just storing dark energy but regulating it, releasing it back into the universe in a slow cosmic drip feed. Even more provocative is the black hole information paradox, which suggests that everything swallowed by a black hole isn't truly destroyed, just scrambled beyond recognition. Some theorists argue this paradox might hold clues to dark energy's origin. If information isn't lost but transformed, the process could generate tiny amounts of repulsive energy, like steam escaping a pressure cooker. Multiply this across billions of black holes across the universe, and suddenly their collective output might match the observed strength of dark energy. It's as if black holes are cosmic batteries, charging and discharging in a cycle we're only beginning to decipher. Critics point out glaring holes in the idea. For one, black holes are too sparse to account for all of dark energy's pervasive influence, and the math linking horizon dynamics to vacuum energy remains speculative, like trying to balance a budget with imaginary numbers. But supporters counter that supermassive black holes at galactic centers could be the missing piece, their immense size making them disproportionately influential. Simulations show their growth over cosmic time might align eerily with the onset of accelerated expansion, like two hands of a clock moving in sync. the most radical implication. If black holes and dark energy are entangled, then the fate of the universe might hinge on how these gravitational behemoths evolve. Will they eventually evaporate, releasing stored energy in a final burst, or could they grow indefinitely, locking away more and more vacuum energy until the cosmos runs dry? The answers might lie in next-generation gravitational wave detectors, which could spot subtle anomalies in black hole mergers hinting at hidden energy exchanges. One thing's certain, if black holes are the universe's secret keepers, they're not giving up their secrets easily. Imagine walking into a cavern so vast its walls lie beyond sight, a hollow so empty, sound itself would fade before reaching the other side. That's the eerie reality of cosmic voids, the universe's most desolate regions where galaxies are almost absent and darkness reigns. But these barren expanses aren't just empty, they're cosmic amplifiers stretching the influence of dark energy to its extreme. While galaxy clusters bustle with gravitational drama, voids are where dark energy's subtle push becomes impossible to ignore, like spotting ripples in a still pond where no stone was thrown. Here's why voids are the ultimate dark energy detectors. In dense regions like galaxy clusters, gravity's pull is overwhelming, masking dark energy's feeble nudge. But in voids where matter is sparse and gravity's grip slackens, the repulsive force has room to flex. Picture a tug of war where one team suddenly vanishes. The remaining side's pull becomes obvious. That's what happens in voids. With gravity's counterweight diminished, dark energy's push dominates, accelerating the void's expansion faster than the surrounding universe. Over billions of years, these voids grow disproportionately, their edges stretching thin like overinflated balloons. The real magic lies in the details. As voids expand, they leave subtle fingerprints on the galaxies drifting along their borders. These galaxies aren't just being carried outward, they're caught in a cosmic tug, their motions revealing the strength of dark energy's push. Astronomers call this the redshift space distortion effect, where the void's growth warps the apparent positions of galaxies in redshift surveys. It's like watching buoys in a whirlpool. Their drift patterns betray currents too faint to see directly. Some voids, like the infamous Boötes void spanning 330 million light-years, exhibit expansion rates so extreme they've been dubbed dark energy tornadoes, flinging galaxies outward like debris in a storm. But voids aren't just passive witnesses, they're time capsules. Smaller voids formed early in cosmic history, while larger ones grew more recently as dark energy took command. By mapping their sizes and distributions, scientists can reconstruct dark energy's rise to dominance, like dendrochronologists reading tree rings to trace climate history. The Dark Energy Survey's void catalog, for instance, exposed a curious pattern. Voids today are 20% larger than predicted if dark energy were constant, hinting it might be strengthening over time. The strangest twist, voids may hold clues to dark energy's nature. If it's a dynamic field like quintessence, voids should grow more irregularly, their edges roughened by fluctuations in the field's strength. If it's Einstein's cosmological constant, their expansion should be smoother, like ink diffusing in water. Future telescopes like Euclid aim to measure void shapes with micron-level precision, searching for these telltale wrinkles. Yet voids guard their secrets fiercely. Some appear underdense even for dark energy's influence, as if something else, hidden structure, modified gravity, or quantum entanglement is at play. Others, like the KBC void, suggest we might live inside a local bubble of emptiness, skewing our cosmic perspective. But one thing's certain, in the silence of these abysses, dark energy's whisper becomes a shout. And if we learn to listen, the voids might just reveal the universe's deepest truth, written not in starlight but in absence. What if the universe's most elusive particles hold the key to its greatest mystery? Neutrinos, those ghostly, nearly massless particles that stream through your body by the trillions every second, might be silently shaping the fate of the cosmos. For decades, physicists assumed these cosmic phantoms were too lightweight to influence anything beyond particle physics. But hidden in their tiny masses could lie a connection to dark energy so profound, it rewrites our understanding of both the quantum world and the universe's expansion. Consider this: neutrinos are shapeshifters. As they travel, they oscillate between three different mass states, like a chameleon cycling through colors mid-step. Now imagine those tiny mass fluctuations aren't just happening in isolation, they're somehow tied to the fabric of spacetime itself. Some theories propose that as neutrinos transition between mass states, they release or absorb energy from the quantum vacuum, subtly tweaking dark energy's strength over cosmic time. It's as if the universe has a dimmer switch, and neutrinos are the unseen hand adjusting it. The math behind this idea is as elegant as it is radical. In the early universe, when neutrinos raced around at near light speed, their mass oscillations could have been frenetic enough to destabilize dark energy, preventing it from dominating too soon. But as the cosmos expanded and cooled, neutrinos slowed down, and their oscillations became more measured, like a pendulum settling into a steady rhythm. This shift might have been the trigger that allowed dark energy to turn on 5 billion years ago, kicking the universe's expansion into high gear. Picture a crowded dance floor where everyone's movements initially cancel each other out until the music slows, and suddenly the collective motion shifts in one decisive direction. Critics argue that neutrinos are too feeble to drive such cosmic scale effects. After all, their individual masses are less than a millionth of an electron's. But supporters counter that neutrinos outnumber atoms in the universe by 1 billion to 1, and their cumulative influence could be monumental. It's the difference between a single raindrop and a monsoon. One is insignificant, but trillions together reshape landscapes. The search for this neutrino dark energy link is already underway. Experiments like the upcoming Deep Underground Neutrino Experiment DUNE aim to measure neutrino mass oscillations with unprecedented precision, hunting for anomalies that could hint at interactions with dark energy. Meanwhile, cosmological surveys are scouring the large-scale structure of the universe for patterns that align with neutrino-driven expansion, the wildest possibility. Neutrinos might not just influence dark energy, they could be part of its very essence, a bridge between the quantum realm and the cosmos's accelerating fate. If proven, this connection would solve two mysteries at once: why neutrinos have mass at all, and what dark energy truly is. But more than that, it would reveal a universe where the tiniest particles and the grandest scales are intimately entwined, where a whisper in the quantum dark can echo across billions of light years. The universe has always been full of surprises, and this might be its most poetic yet, that the ghosts within us hold the secret to the void beyond. Could the same force that sent the newborn universe hurtling outward at unimaginable speeds also be responsible for tearing it apart today? The theory of cosmic inflation, a trillionth of a second when space itself expanded faster than light, has long been considered separate from dark energy's modern reign. But what if these two epochal events are really just different chapters of the same cosmic story? Think of it like a pendulum with an unimaginably long swing. Inflation would be that first violent jerk, the initial push that set everything in motion. Then, for billions of years, gravity dominated as the cosmos settled into a slower rhythm of expansion. Now, dark energy appears to be pulling the pendulum back up again, accelerating the universe toward some unseen climax. The tantalizing possibility, both inflation and dark energy, might stem from variations of a single, overarching field woven into spacetime itself. A cosmic actor playing different roles across an unimaginable span of time. The math behind this idea gets dizzying fast. Inflation is thought to have been driven by an inflattened field, a temporary surge of repulsive energy that smoothed the universe to near perfection before fading away. Dark energy, by contrast, behaves like a faint but persistent echo of that initial push. Some theorists suggest these could be different states of the same fundamental field like water existing as both crashing waves and still vapor, depending on the conditions. In the searing heat of the Big Bang, this field's energy density would have been enormous, driving inflation. As the universe cooled, the field might have frozen into a lower energy configuration, becoming the dark energy we detect today. Here's where things get strange. If inflation and dark energy are linked, it could mean our universe is caught in a cycle of expansion pulses, each one weaker than the last, like ripples fading in a pond. Some models even suggest dark energy could eventually decay, triggering a new inflationary phase billions of years from now. Picture a slumbering volcano, quiet for epochs, but capable of reawakening with world-shaping force. Critics point out glaring differences between the two phenomena. Inflation was absurdly brief and immensely powerful, while dark energy is feeble but persistent, like comparing a supernova to a candle. Yet supporters counter that quantum fields can exhibit radically different behaviors under different conditions. The Higgs field, for instance, gives particles mass today but may have sparked cosmic phase transitions in the early universe. The most compelling clues might lie in gravitational waves. Primordial ripples from inflation could carry imprints of the inflated field's properties, while future detectors might spot subtle shifts in dark energy's influence on modern spacetime. If both signals align, we could be looking at the same cosmic fingerprint pressed into opposite ends of time. Until then, this idea remains a beautiful speculation, one that ties the universe's first breath to its last gasp. Whether it holds up or not, the mere possibility forces us to confront a profound truth. The cosmos may not just change over time, but remember its own beginnings. And if dark energy really is inflation's distant descendant, then the universe isn't just expanding, it's rediscovering itself. Every measurement we take of the cosmos assumes the laws of physics hold true across time and space. But what if dark energy plays by different rules depending on when and where we look? This is the heart of the running lambda problem, a technical headache where dark energy's influence appears to shift across cosmic epochs like a phantom changing costumes. Lambda, the symbol Einstein gave to his cosmological constant, was meant to represent an unchanging force, yet mounting evidence suggests it might be a moving target, its strength waxing or waning over billions of years. It's like trying to predict the weather with a barometer that mysteriously recalibrates itself when you're not looking. The first cracks in Lambda's steadfast reputation came from supernova surveys. When astronomers compared explosions from 9 billion years ago to those occurring more recently, some datasets hinted that dark energy's push was weaker in the ancient universe. Imagine digging through layers of tree rings and finding that younger trees grew faster despite identical soil conditions, except here, the soil is spacetime itself. Then came measurements of baryon acoustic oscillations, the fossilized ripples from the early universe's sound waves. These cosmic yardsticks suggested the universe expanded more slowly in certain eras than Lambda's constant value predicts, as if dark energy took a cosmic coffee break before resuming its work. But the real plot twist emerges when we examine quasars, the brilliant beacons powered by supermassive black holes. Their light, filtered through clouds of intergalactic gas, acts like a time-stamped receipt for the universe's expansion rate. One controversial analysis claimed that around 8 billion years ago, dark energy's strength might have briefly spiked, like a hidden second engine kicking in during the cosmos's middle age. Skeptics argue this could be an artifact of dust obscuring distant quasars or systematic errors in interpreting their spectra. But if verified, it would mean Lambda isn't just a dial set once at the dawn of time, it's a knob being turned by invisible hands. The implications ripple through every corner of cosmology. If Lambda runs, then dark energy isn't a passive backdrop but an active participant in the universe's story, evolving alongside galaxies and black holes. Some theories propose this variability could stem from dark energy's quantum nature, a field that decays like radioactive material, losing potency as the cosmos ages. Others suggest it might interact with dark matter through undiscovered forces, like two dancers subtly influencing each other's steps across the eons. The wildest possibility, lambda's fluctuations could be evidence of a multiverse, where our patch of space inherits its dark energy properties from a higher dimensional collision we'll never see. For now, the running lambda problem remains a battleground of competing datasets and interpretations. Upcoming projects like the Dark Energy Spectroscopic Instrument aim to settle the debate by mapping millions of galaxies across 11 billion years of cosmic history. Because if lambda isn't constant, we're not just refining a number, we're witnessing the universe rewrite its own rulebook in real time, and that changes everything. When the Large Hadron Collider roared to life in 2008, physicists held their breath not just for the Higgs boson, but for something far stranger. Among the shower of particles produced in those high-energy collisions, some dared to hope they might catch a fleeting glimpse of dark energy itself. Imagine throwing two watches together at unimaginable speeds, hoping the wreckage would reveal the secret of time. That's the scale of ambition behind this cosmic detective work. The logic was tantalizing. If dark energy stems from quantum fields or hidden dimensions, the violent collisions of protons might briefly wrench open portals to those unseen realms, leaving behind traces no telescope could ever spot. Reality, however, proved stubborn. Despite smashing particles with energies replicating the universe's first trillionth of a second, the LHC found no exotic particles matching dark energy's signature. No sudden bursts of unexplained energy, no hidden dimensions curling into view, no strange new forces acting at microscopic scales. It's as if the collider was shouting questions into the void, only to hear its own echo in return. But the silence speaks volumes. Here's why these failures are anything but. The LHC's empty hands forced physicists to confront an uncomfortable truth. Dark energy might not be a particle at all, or at least not one accessible at energies we can muster. Think of it like trying to recreate a hurricane by splashing water in a bathtub. Some phenomena exist only at scales too vast or energies too faint to replicate in a lab. The collider's limits suggest dark energy's secrets are locked in physics beyond the brute force approach of particle collisions, hiding in the subtleties of spacetime itself rather than the debris of shattered protons. Yet the hunt isn't over. Some theorists argue the LHC might still hold clues hidden in plain sight. Quantum entanglement experiments using the collider's detectors could reveal if spacetime has an underlying granularity linked to dark energy's effects. Others propose that dark energy particles, if they exist, might be so weakly interacting that they slip through the LHC's sensors like ghosts through walls. It's like searching for a whisper in a thunderstorm. The signal might be there, drowned out by the noise. The most radical idea, the LHC's true contribution to the dark energy puzzle, might be negative results. By ruling out entire classes of theories, extra dimensions large enough to detect certain types of supersymmetric particles, it's funneling physicists toward bolder, more imaginative solutions. Sometimes knowing where not to look is the first step to finding what's really out there. And in a mystery as deep as dark energy, every dead end is a signpost pointing toward stranger possibilities. What if our search for dark energy is doomed from the start, not by flawed methods, but by the very laws of existence that allow us to search at all? This mind-bending concept, known as the anthropic shadow, suggests we might be staring at a cosmic hall of mirrors where every observation is distorted by the simple fact that we're here to make it. Imagine walking into a library where every book you can reach happens to be written in your native language, not because other languages don't exist, but because you'd never notice the shelves filled with scripts you can't read. That's the paradox haunting dark energy research. We can only measure its value in a universe where its strength permits galaxies, stars, and ultimately, curious minds like ours to exist. The numbers tell a chilling story. Calculations show that if dark energy were just slightly stronger, by a factor as small as 10, the universe would have expanded too rapidly after the Big Bang for galaxies to form. No galaxies means no stars, no planets, no observers. On the flip side, if dark energy were weaker, gravity might have crushed everything back into a singularity before life could emerge. Our universe's dark energy value sits in an absurdly narrow sweet spot between these catastrophes, like a needle balanced on a razor's edge. The question isn't just why this balance exists, it's whether we're fooling ourselves by expecting any other outcome could ever be observed. Critics dismiss this as a philosophical cop-out, a way to avoid wrestling with the deeper why. But supporters point to concrete examples where selection effects warp our perception. Take meteor impacts. The fact that we don't see civilization-ending asteroids hitting Earth every century doesn't mean they can't happen. It just means we're more likely to evolve during the long, quiet gaps between catastrophes. Similarly, our cosmic neighborhood might be a statistical fluke, one bubble in a frothing multiverse where most regions are either barren wastelands or collapsed husks. The eerie fine-tuning of dark energy could simply be our address in a much weirder reality. Yet the anthropic shadow isn't just a thought experiment, it has measurable consequences. If our universe is one of many, certain anomalies should lurk in the cosmic microwave background, subtle scars from collisions with other bubble universes in the distant past. Some researchers claim to have spotted these fingerprints in Planck satellite data, unusual cold spots and asymmetries that defy standard explanations. Others argue these are statistical mirages, cosmic Rorschach tests where we're seeing patterns in the noise. The stakes couldn't be higher. If the anthropic principle holds, dark energy's value isn't a puzzle to solve but a selection effect, one that redefines what science can even ask. But if it's wrong, we're left with a coincidence so staggering it begs for a deeper explanation. Either way, the universe is playing a trick on us, hiding its greatest secrets not in darkness, but in plain sight, where only observers like us can be fooled by them. What if everything we think we know about dark energy is just a trick of the cosmic light? A growing chorus of physicists is daring to ask the unthinkable, that this mysterious force driving the universe apart might not exist at all. Instead, they argue, we could be staring at the universe's greatest mirage, a collective delusion born from our own limited perspective. Picture standing in a vast desert, convinced you see water shimmering on the horizon, only to realize it's just heat distorting the air. Now imagine that illusion scaled up to cosmic proportions. Our galaxy, it turns out, sits inside a sprawling underdense region called the KBC void, a bubble of relative emptiness stretching over 2 billion light-years across. In this scenario, the accelerated expansion we attribute to dark energy might simply be the void's gravity tugging us outward, like a rubber band snapping after being stretched too far. Local measurements would show galaxies fleeing faster than expected, while the wider universe expands at a steadier pace. It's as if we've been measuring the wind speed from inside a hurricane's eye, mistaking local chaos for a global storm. But the illusion might run deeper still. Some theorists propose that dark energy isn't just a measurement error. It could be a mathematical artifact, a glitch in how we stitch together Einstein's relativity with quantum mechanics. Think of it like using 19th century physics to describe a superconductor. The equations might spit out nonsense not because nature is wrong, but because our tools are too crude. When cosmologists account for the universe's uneven distribution of matter, its dense galaxy clusters and gaping voids, they often rely on approximations that smooth everything into an imaginary average. But what if that mathematical shortcut is erasing crucial details, like a cartographer flattening mountain ranges into featureless plains? the resulting equations might demand a dark energy term to balance the books, when in reality, we've just misapplied the math. Even more radical is the idea that dark energy could be an echo of our cosmic origins. Inflation, the universe's explosive birth, left behind ripples in space-time that might still influence expansion today. If those primordial waves interact with modern structures like galaxy filaments, they could mimic dark energy's effects, like an orchestra's opening chord resonating faintly through the entire symphony. This wouldn't just demote dark energy from a fundamental force to a side effect. It would weave the universe's beginning and present into a single, unbroken story. The stakes of this debate couldn't be higher. If dark energy is an illusion, we've spent decades chasing a phantom, but if it's real, dismissing it could mean missing the cosmos's deepest truth. Future galaxy surveys and precision tests of gravity aim to settle the matter, probing whether the universe's acceleration is truly universal or just a trick of our lonely vantage point. Until then, one haunting possibility remains, that the greatest force shaping reality might not lie in the dark between stars, but in the shadows of our own understanding. After this whirlwind tour through the cosmos's greatest unsolved puzzle, one thing becomes painfully clear: dark energy isn't just a gap in our knowledge. It's a yawning chasm, swallowing every assumption we've ever made about how the universe works. We've chased phantom forces through tangled equations, stared into voids that defy logic, and wrestled with numbers so mismatched they border on absurdity. And yet, after decades of searching, we're still left with more questions than answers. Does dark energy hide in extra dimensions we can't perceive? Is it the dying breath of an inflattened field from the dawn of time? Or could it all be a grand illusion, a cosmic sleight of hand tricking us into seeing acceleration where none exists? The sheer audacity of these mysteries should leave us humbled. Here's a force making up nearly 70% of everything in existence, and we can't even say whether it's a particle, a field, or a flaw in our understanding of gravity itself. Einstein's equations, once the unshakable foundation of cosmology, now creak under the weight of these enigmas, hinting that relativity might only be part of a much weirder story. Solving this puzzle won't just require new math, it demands a revolution in how we conceive reality. Imagine explaining smartphones to a medieval scholar. The truth about dark energy might be equally incomprehensible from our current vantage point. But here's the exhilarating part: we're living through the detective story. Every anomalous galaxy cluster, every whisper from the cosmic microwave background, every lab experiment probing quantum foam is another clue waiting to crack this case wide open. And when it finally happens, when some brilliant mind pieces together the truth, it won't just rewrite textbooks, it'll redefine our place in the cosmos. So tell us, which theory keeps you up at night? The multiverse's infinite dice rolls, black holes hiding dark energy in their event horizons, or something wilder still? Drop your favorite ideas in the comments, because the next great breakthrough might start with a spark of imagination from someone just like you. After all, the universe's greatest secrets don't give themselves up easily. But that's what makes the hunt so thrilling.